I'll be your guide through this course and its many lessons. We're currently reviewing the structural mechanics lesson. We're on the sixth recording, or the last recording of the lesson. Each of the recordings lasts approximately about 1 hour, so please use that time frame to plan your study schedule. So let's continue with the structural mechanics lesson. The causal material now is that of slabs. So let's talk about the design of slabs and their deflection limitations. So what are slabs? Their lengths and widths are large in comparison to their thickness. Their thickness is covered by deflection criteria or by fire rating requirements. They're generally classified as either one or two-way slabs. Their longitudinal reinforcement is designed to resist bending moments. Slabs are commonly constructed from reinforced concrete, except for low-rise wooden residential building foundations and where you have inaccessible roofs. One or two-way slabs refer to whether the slab carries a load in one direction or two directions. One-way slabs typically occur when the span of the slab is relatively small compared to the width of the slab. You will see figure 51.1 from CERN that shows us a detail of a one-way slab. Note how the width of the slab is small compared to its length. That's why this slab carries loads in one direction. A one-way slab has a unit width strip that is taken parallel to the short direction, and the one-way slab is treated as a beam of unit width. That's its unit width strip is treated as a beam of unit width. Now figure 51.1. We can see the slab on a plan view, and then we can see the slab on a section view based on that unit width strip. So that one unit width strip is treated as a beam. And this is the model used to obtain moments and shears within that slab. Note how this connection serves as a connection. Then each one of these serve as a roller connection, or are modeled as a roller connection. The unit width beam is designed for flexion. Shear resistance is typically provided by the concrete alone. Deflections can be calculated using the unit width beam. The torsional restraint introduced by the supported beams is typically neglected. In addition to figure 51.1, table 51.1 shows the minimum thickness of a slab unless deflection calculations are performed. The thicknesses in this table are driven by serviceability criteria rather than strength criteria. And when we talk about serviceability criteria, we're talking about deflection. That's another key technical synonym that you may be tested on in the breadth portion of the PE exam. Here we have table 51.1 from CERN, which provides you with minimum thicknesses for one-way slabs. Now in the left column you can see the type of construction for the slab. If it's simply supported, if it's continuous in one end, if it's continuous in both ends, or if it is a cantilever slab. And you see the deflections, the minimum thicknesses based on the span length. So if your span is 20 feet, then your slab thickness needs to be 1 over 20 over 20 needs to be 1 foot. Now for two-way slabs. The ratio of long to short sides is smaller than 2, and the slab system and supporting columns are reduced to a series of one-dimensional frames running in both directions. Figure 51.3 shows you a detail of a wide beam frame, which is used in the analysis of a two-way slab. As figure 51.3 shows, the beams in the frames are white elements whose edges are defined by the way between the columns. Two-way slabs are not common in breadth exam problems, except you may have broad conceptual problems that do not require detailed analysis. Figure 51.2 of SERM has some examples of two-way slabs. Waffle slabs are used in large spans, up to about 30 feet, where drop beams are not structurally acceptable. Table 51.5 of CERN shows minimum thicknesses for slabs without interior beams. It is difficult to obtain accurate estimates of deflections in two-way slabs. In practice, rather than attempting to calculate deflections accurately, two-way slabs should be sized to satisfy the minimum thickness values given in the ACI Code 318 under the section 9.5.3. Since deflection calculation requires special finite element analysis, it is common practice for slab thicknesses to be below the values given in the table. Here is another key table that you may want to tab as a reference to use during the exam. Table 51.2 of CERN shows you the average steel area per foot of width for the slab. And what is key here is that this table gives you the bar size number you may be using to reinforce your slab. It gives you the spacing of the bars in inches, and it provides you the average steel area per foot width of the slab. Another key part of the slab is that it provides you the nominal diameter in inches for each bar size number. Note that the bar size number is based on 1/8. That's why your bar size 8 is going to have a nominal diameter of 1 because it'll be 8 over 8. Now, how can you use this table in the P exam? You may be asked a problem on a one-way slab or on a reinforced concrete slab, and you show the dimensions of the slab and you show the reinforcement, and you're simply asked to calculate the average steel area per foot width of the slab. So you can simply come to this table and find that solution. If for some reason your number or the spacing lies between the number shown here on the table, you can interpolate in between. And here we see figure 51.2 that provides us details of descriptions, graphical descriptions of two-way slabs. Now, two-way slabs may not be encountered in the test in the breadth portion of the test. for you to, solve a problem on the design of a two-way slab. However, you may be provided with a figure that tells you a flat plat, a flat slab, a waffle slab, or a two or the description of a two-way slab with beams. And you may need to identify which one is a two-way slab and which one functions as a one-way slab. Here we see table 51.5 of CERN, which provide you with the minimum thicknesses for slabs without interior beams. Here you can see that on the left column, the yield strength of the concrete. It's 40,000 psi, 60,000 psi, or 75,000 psi. You can see if the slab has drop panels or does not have drop panels. You can see the exterior panel in inches and interior panel in inches. And then if the slab has edge beams or does not have edge beams. And with that, you have the minimum thickness for slabs. Which are given in inches. So that's it for two-way slabs. Now we're going to move into the concept of the design of columns. In general, we consider the design of columns. We'll cover some of these topics. Now, columns are vertical members. Columns are always going to be vertical members. The primary purpose is to transfer axial compression loads to the foundation. The primary purpose of columns is to transfer that axial compression that they've gathered through either beams or slabs down to the foundation. And columns may be subjected to both axial compression and to significant bending moments. Now, the P minus delta effect is the factor that may increase column loads. The increase in moment that results when the column sways, which adds eccentricity. Columns where the P minus delta effect is significant are known as long or slender columns. And slender columns will be outside of the scope of the breadth portion of the exam, and of course, outside of the scope of this refresher course for the exam. Now, Euler's column buckling theory for column design and analysis applies to an ideal column, which is initially perfectly straight. The column is isotropic. It is free of residual stresses. It has spin on both ends, and it is concentrically loaded. So we have here equation 61.1 from CERN that provides you with the Euler buckling load. When loaded to the buckling load or the Euler load, a column will fail by sudden buckling or bending. The Euler load theory applies to all materials. However, it is applied in a slightly different way for each material, as per the specifications given by the respective institute, such as ACI for concrete or AISC for steel. Now, short concrete columns are part of brace structures and are considered short columns if we have equation 52.1 holds the slenderness ratio criteria. Now braced columns need to follow the conditions shown in equation 52.1, and unbraced columns need to follow the conditions shown in equation 52.2. N1 equals the smaller of the two end moments acted on a column, and it's the smaller in absolute value. Please, if you have a negative moment, it just simply means that the moment is going in the opposite direction. It does not mean that he has a less moment or lesser bending force. M2 will be the larger of the two end moments acting on a column, again, based on absolute value. So you can have a larger bending moment that is a negative moment. The value K sub B L sub U over R is a column's slenderness ratio. Now, if inspection cannot determine whether a column is braced or unbraced, ACI 318 under section 10.10.1 permits a column to be considered braced against side sway if the bracing elements in that story have a total stiffness resisting the lateral moment of the story of at least 12 times the gross stiffness of the columns within that story. Now, there are many different specifications within the different codes, such as the ACI 318, the American Concrete Institute 318 guideline. However, for the P exam, especially for the breadth portion of the exam, you do not need to be familiar with all these different code-specific requirements. However, you do need to be familiar with the different equations to calculate the different moments, slenderness ratios, and evaluation whether a column is braced or unbraced. Now, section 53.2 within CERM will provide you a little bit more information regarding the bracing of concrete columns. So you're more than welcome to review it to get additional information. Short concrete columns that have small eccentricity. Now we have the normalized eccentricity, which is the ratio of the maximum moment on a column to the product of the axial load and the depth of the column. The design of a column for small eccentricity is based on equation 52.7 of CERN. So let me zoom in so you get a better look at the equation. For tight columns, phi equals 0.65 and beta equals 0.80. For spiral columns, phi equals 0.75 and beta equals 0.85. Small eccentricities occur when normalized eccentricities are less than 0.05 for spiral tight columns and 0.1 for tight columns. Now we see the additional equations on CERM which go from equation 52.8 through 52.10 that deal with the small eccentricity of short concrete columns. So I'm zooming in so you can get a better look at them. And tight columns fail in a relatively brittle manner. Spiral columns, having a better confinement of the core, undergo significant deformation before significant deterioration of the load carrying capacity ensues. The more ductile failure mechanism of a spiral column is illustrated by comparing the phi and the beta factors for the tight and for the spiral columns. Now, let's talk about steel columns. Steel columns are relatively stiff members, which are generally required. Rods, bars, and plates are commonly used as tension members. They're too slender. Steel columns are too slender to be used as compression members, and unless they are very short or lightly loaded. For building columns, W shapes with nominal depths of 14 inches or less are commonly used. These sections typically have a relatively square outline shape and are more efficient than most others for carrying compressive loads. Figure 61.1 of CERN shows the cross-section of typical compression members. Load carrying capacity varies approximately inversely with the slenderness ratio. There are three general modes by which axially loaded compression members can fail. 1. Flexural buckling, which is also known as Euler buckling, which is the concept that we just reviewed. 2. Local buckling, where one or more parts of the member cross-section fails in a very small area. And 3. Torsional buckling, where lateral movement and twisting occurs. Here's figure 61.1 from CERN, which shows us the typical compression members cross sections, members are typically used as compression members in a steel design. So we have first a single angle, then a double angle, then a T, a channel, a W column, a pipe, can be either a round, square, or rectangular tubing. We have a 4-angle box section, then a box section made with channels, a box section that is shown opposite made with channels, then another box section with a plate and 2 channels, and then a box section that's built out of 4 single angles and a few plates, then a W that has additional cover plates, then a built-up section just made out of plates, a built-up square tubing that's just built out of plates, a W that's been added channels to increase the inertial moment at the flanges, then a built-up section that's made of plate and 4 single angles, and another built-up section that's also made out of a plate and 4 single angles with 2 additional plates at the flanges. Now the design of steel columns. The column section properties referred to as major and minor axes. For doubly symmetric columns, the Fy moment of inertia is smaller than the Ix. The Iy moment of inertia is smaller than the Yx. Column buckling about the minor axis if the failure mode is shown in figure 61.3. Bracing restraints against lateral displacement. And in figure 61.3, we can see the minor axis buckling and bracing. Under portion A, we can see minor axis buckling, and on option B, we can see minor axis bracing to prevent the buckling along the minor axis. Doubly symmetric shapes are shapes which have 2 axes of symmetry. Since buckling about the minor axis is the expected buckling mode, bracing for the minor axis is usually provided at intermediate locations to reduce the embrace length of the column. Here we see the slenderness ratio, which is known as SR, and this is used to categorize steel columns as either long columns or intermediate columns. So let me zoom in so you can get a better look. And this is equation 61.5 of CERN. And K equals the effective length factor, L equals the actual length, and R equals the radius of gyration. The SR of compressive members preferably should not exceed 200, and this is per the AISC specifications shown in section E2. The limit on the SR is partially due to constructability concerns. Therefore, the SR at time will exceed 200. Here we have table 61.1 of CERN that shows the effective length factors for steel columns. So we have the description of the two different ends at the column. We have one end is a built-in and another end is another built-in. Then we have the effective length factor for that type of column. If one end is built-in and the other one is spin, then our effective length factor is going to be 0.80. If one end is built in and the other end is fixed to rotation, but it allows for translation, then our K factor is going to be 1.2. Our highest K factor will be when we have one end of the column built in and the other end is completely free. It can move for rotation and it can move for translation. So that will give us a 2.1 effective length factor. Now when we have a column that's spin on both ends, that effective length factor is going to be 1. If it's spin in one end and it's fixed for rotation and it's translation free on another end, that will give us our second largest K value, which will be 2.0. Note the smallest value is 0.65 when you're restraining the column at both ends for both rotation and translation. And when you have the column pin in both ends, they're only fixed for translation, so that is only 1.0. Now note that these values are different from the theoretical values which are often quoted for use within Euler's equation. Now the values used in table 61.1 can be used in preliminary design, where the dimensions of the members are not yet determined. The effective length factor is based on the end conditions of a given buckle. These end conditions dictate the buckle shape of the column. Now the effective length factor, which are the precise values, are determined with end condition coefficients, either GA or GB, based on your end condition. And this can be determined from equation 61.4 of CERN. For ground level columns, one of the column ends will not be framed to the beams or other columns. In that case, G will equal to 10. Will be used for pin ends, and G equal to 1 will be used for rigid footing connections. Figure 61.2 of CERN shows precise values of the effective length factor. The alignment charts are symmetrical. Either end can be designated A or B. The subscripts in equation 61.4 refer to the column and beam framing into the end of the column. Now here we have figure 61.2 of CERN, which shows us the effective length factor alignment chart. So we know the G's for either side of the column. We can find the K value for that specific column. Now please note that this chart is divided into two segments. The top segment is used for sideway inhibited columns, whether the bottom segment is for sideway uninhibited type of columns. So simply you just connect, once you find your G values for each end of the column, simply connect the two, and that will give you your K value. For this example, that will be 3. The theoretical Euler stress, which is the actual stress, is lower due to imperfections, and the theoretical Euler stress can be found using equation 61.3 of CERN. And this is based on the steel manual's specification equation E3-4. Let me zoom in so you can get a better look at this equation. Now F sub E equals the theoretical Euler stress. The actual stress can be seen in figure 61.4 of CERN. Now, the imperfections that are included are the geometric tolerances, the material property variance, and the boundary condition fixity, which is assuming a pin-to-pin column where each end actually has a small rotational restraint on it. Now here we have figure 61.4 that shows us the actual compressive stress versus the slenderness ratio. Now on the vertical axis, we can see the flexural buckling stress, while on the horizontal axis, we can see the slenderness ratio. Note that on the left portion of the diagram is what we will have inelastic buckling, and that is governed using equation 61.6 of CERN. Note how on the right part of the diagram we will have elastic buckling, and that will be governed by equation 61.7. And the transition between inelastic and elastic buckling is given by 4.71 times the square root of E over F sub Y. Now, the buckling of real columns. You will use Euler's buckling law formula, which deals with concentrically loaded ideal columns, which might be difficult to achieve in the real world. Now, for real columns, they will have flaws, they'll have curvature, variations in material properties, and residual stresses. Therefore, concentric loading will not be possible. So what is done is you design compressive strength that is lower than the Euler stress. Residual stresses are of particular importance with slenderness ratios of 40 to 120, a range that will include a very large percentage of the columns used in design. And here we have a better look at figure 61.4, with the two equations 61.6 shown at the bottom. F sub CR, which is the F critical, is the ultimate stress of the steel material in the specific condition used in the calculation. Now, this concept might be in the breath exam as a conceptual question rather than a full numerical problem. Commonly, the allowable stress will be given in the exam, as we will see in our next problem. So here we have problem number 7 of our structural mechanics lesson. So let's put to practice the concepts that we have reviewed so far. The short column shown has a square cross-section and carries a maximum concentric load of 100 kilonewtons. The allowable strength of the column material is 100 kilonewtons per square meter. Here we see the short column with the 100 kilonewtons concentric load being applied on top of it, and how the column rests on a foundation, which can be interpreted as a spread footing. Now, what we're going to ask is, what is the minimum required side length of the square? Is it half a meter, 1 meter, 1.5 meters, or 2 meters? Half a meter, 1 meter, 1.5, or 2 meters? If you would like to solve this problem on your own using the concepts that we have reviewed so far, please go ahead and pause the video at this moment. Now, this problem requires you to recognize what it means to be a short column. Short columns will crush before they reach to buckling. So when you have a short column, you do not evaluate for buckling equations. So that is a key distinction that will help you quickly solve a problem in the PE exam. So if you encounter with a short column, instead of going through the different buckling evaluations, you can skip those because the column will crush before it buckles. So let's go through the solution. Now, from the information that we were provided, we know that the maximum is 100 kilonewtons, which is our maximum concentric load, or maximum, allowable strength of the column is 100 kilonewtons. Being compression. Since the force is concentric, we have that the moment is going to be equal to 0 because there's no eccentricity in the column. The load is perfectly centered, and we're not told anything otherwise in the problem prompt. And with information given, we really cannot determine if there's any eccentricity in the column. So this is a very, very safe assumption. So then we go through and we calculate the maximum normal force and then bending moment for the column. So here we calculate the maximum normal force and bending moment for the column. Now, because this column is only functioning in compression, we can say that the stress of the column is going to be equal to that compressive load over the cross-sectional area of the column. Now, the maximum stress allowable on that column is going to be equal to its maximum compressive strength over the area of the column. Because the column is square, we can say that the area is going to be the thickness times the thickness, which is the thickness squared. Right? The area of a square is the two sides multiplied together. So that's why if we use the maximum axial load divided over the cross-sectional area of the column, we'll get our maximum allowable stress. And we're given the maximum allowable stress as 100 kilonewtons per square meter. And we're given the maximum allowable load as 100 kilonewtons. So then we can grab this part of the equation I didn't mean to put any field with that. Let me try again. Oh wow, this is not playing nice today, is it? I think I got it now. So you grab this part of the equation and you solve for t. Now, because t is squared, to solve for t, we need to get all this to the square root. And that's how we solve for this equation. We have 100 kilonewtons over 100 kilonewtons per square meter. Then that's going to equal to 1 square meter. So when we do the square root of 1 square meter, that's going to equal to 1. Now the problem may ask, perhaps, provide you units in centimeters or millimeters. And then you will need to convert that to those specific units. So that's how we solve for this problem. Now the example does not specify the material used, and it doesn't require deep knowledge of the design procedure for any kind of material, which is a very common way of testing for these concepts in the breadth portion of the exam. Now, in the depth portion of the exam, you will need to know some additional information on the material to solve for a bit more complex type of problem. So if you're taking the depth portion of the exam in structural subdiscipline of civil engineering, you will need to consider or take this into account. Now, often a minimum eccentricity must be assumed in column design. Now, when we have a short column, the minimum eccentricity does not typically induce buckling. Rather, it will cause flexural stresses in addition to the normal stress in the column. Here we have Appendix 58.A of CERN, which also provides you some information about common structural steels that may be used. The reason I bring this up is because you may be tested a theoretical question on, if you know, on the use of a steel, or you may be required to look up the minimum yield stress for a specific steel material. Plus, this can also give you some additional information. Now, A36 is a carbon type of steel, and it's typically used for shapes, bars, and plates. And we say shapes would be like a W shape, like an S shape, and so forth. And the minimum yield stress of A36 is 36 KSI. For A52.9 is 42 to 50, A57.2, 42 to 65, A242, 42 to 50, A58.8, 42 to 50, A852, 70, and A51.4 for 90 to 100, and last A992 from 42 to 65. So please note that only A36 is the one that has a yield stress similar to the number that's shown right next to the A letter. And you also can get the minimum tensile strength for this type of steel. Let's look at one more problem when it comes to columns. So here we have an example. This is from the practice exam offered by PPI. A solid masonry column has a cross-section measuring 32 inches by 32 inches. The column is subjected to axial compression force of 110 Gibbs, which includes the weight of the column, and it has an eccentricity of 5 inches about one axis. What is most nearly the maximum compression stress caused by this loading? Is it 0.2 Gibbs per square inch, 1.3 Gibbs per square inch, 2.4 Gibbs per square inch, or 3.0 Gibbs per square inch? If you would like to solve this problem using the concept that we have reviewed so far on your own, please go ahead and pause the video at this moment. Now, one of the key things on this problem is that we're being told that this is a masonry column. a solid masonry column, we're given kind of like some kind of information on the material. Let me say that that is thrown as a distractor in this problem. You really do not need to know anything specific about the material to solve for the problem. See, they're not telling you in the problem if there's maximum allowable stress or to design for a specific yield stress for the concrete or yield stress for the masonry or yield stress for the steel. So there's nothing here specific on the material. Therefore, this is simply an exercise of understanding how a column member is being loaded and how eccentricity applies to that type of loading. So now the first thing that we need to notice on the problem is that the resulting compression force acts within the middle 1/3 of the cross-section. So the gross cross-sectional area is effective in resisting the combined axial and bending stress. The resultant compression force acts within the middle 1/3 of the cross-section. Within the key critical part of the cross-section. That is one of the first things you need to analyze.